Hello everyone, welcome back to my channel, Predicting the Future. Today we're going to talk about probability measures, and our focus today is Borel Cantelli Lemmas. There are two lemmas in Borel Cantelli Lemmas that's widely used in probability theory, and it's very important lemmas. So let's begin our topic today. First of all, I want to first talk about two random variables. They're very important random variables in stochastic process. The first one is so suppose AN is a series of events belongs to sigma field F. If we define the limsup of AN to be the intersection and union of AN, and if we also define liminf of AN to be the union and intersection of AN, then these two are also random. These two events also belongs to the sigma field F. So what does limsup of AN means? Think about an element omega. This shouldn't be epsilon, so this is a typo here. Omega belongs to limsup of AN. It means that if and only if for every n there exists a k greater than or equal to n such that the omega belongs to a k, or well, another way of saying that limsup over n means that the omega element omega belongs to infinitely many ans. May not be every an, but it will infinitely many ans. So whatever m we start with, we can always find a number n greater than or equal to m that omega belongs to that union of this one, or belongs to one of the ans. So that's called limsup. Or let's go. So if n is time, then limsup of n is often interpreted as a set of elements that happens infinitely many an. So limsup of an is usually written as an I dot o dot, which means infinitely often. The liminf of an liminf of an means that the omega belongs to all but finitely many an. So there's only finite number of an that doesn't contain omega, and starting from some point, all the ans afterwards will contain omega. So that's the meaning of the liminf of an, and usually we write it as an ea, which means eventually all. So eventually the omega belongs to all the ans starting from some point. So let's further look at some of the equations here. So limsup, the inner union of the limsup it's a union set. And this will go. This cell will decrease as m goes to infinity. This cell will be less and less ans that in this union. So it's a decreasing set. It will decrease to its limit, which is the limsup of an. And on the other side, liminf, the inner side of the liminf is the intersection of an. And as m goes to infinity, this intersection will be less and less ans to intersect with each other. Then this set will be increasing, and will increase to the liminf of an. And also, what we can see is that the intersection for AK is always included, is only always a subset of the union of AK for all n and m. So the limsup, so the liminf of an is always a subset of limsup of an, and the complement of limsup of an is actually the liminf of an complement. This is just taking the, when we take the complement of the set, all the union and intersection will just change signs, becomes union and intersection, and the inside will become as the complement. So that's the this one. So now we are ready to talk about our Borel Cantelli lemma. The first Borel Cantelli lemma is this. So if the summation of probability of an is finite, then the probability of an that happens infinitely often has probability 0. So the proof is easy. So limsup of an is included in the union of ak from m to infinity, which implies that the probability of limsup of an is less than or equal to the probability of union from ak from m to infinity, and that is less than or equal to the summation of pak from m to infinity. And the sum goes to 0. The summation goes to 0 as m goes to infinity, so the probability of limsup of an is 0. That's first Borel Cantelli lemma. The second Borel Cantelli lemma is so let an here, there's some difference here. We are not assuming an to be independent here, but in the second one we are assuming that an is a sequence of independent events. And in that case, if the summation of a probability of an is infinity, then the probability of an that happens infinitely often has probability 1. And the proof is so the proof, let's prove it. So to prove that this is 1, we prove that the complement of that is 0. So the complement of limsup of an is just liminf of an complement, which is an complement eventually or event. So that's what we want to prove. We want to prove that to be 0. So for n and m, which are positive numbers, and because since 1 minus x is less than to e to the power minus x, that's I won't explain too much about that. Just draw the graph, you'll see that. So for that n and m, the probability of the intersection of an complement from capital N to M, because they are independent, an are independent, an complement also independent of each other. We didn't mention that in the early things, but so it will go through a little bit more about pi lambda systems and how a pi system will generate a lambda system and those things. So the independence of a pi system indicates independence of a sigma field that generated by the pi system. So anyway, so that's a little bit more mathematical, analytical stuff, and I try to avoid, if I can, I try to avoid those things in here. So just remember, if an is a sequence of events that are independent, then the complement of them are also independent. So that is just because they're independent, we can write as some product of 1 minus the probability of an. And because of this one, 1 minus x is less than e to the power minus x, then that is just e to the power minus the summation of all all the terms here from n to m, probability of an, and that goes to 0 as m goes to infinity. So that tells us that the probability of intersection of an to the complement from capital N to infinity has a probability 0 for all n, all capital N. And since this intersection is a set that increases to the liminf of an complement, as n goes to infinity, we get the limit of that set is equals to the probability liminf of an is an complement, and that's 0. So that proves our second Borel Cantelli lemma. And that's the end of today's topic. Thank you, everyone. Bye.